Okay, thank you, and hello, everyone. My name is Greg Sinnett. I'm a postdoctoral researcher at the University of California, Irvine, where I primarily study coastal ocean processes. One of the ways that I do that is by measuring ocean temperature in ways that inform us about water mixing, transport, and other important physical aspects. Ocean warming is a significant challenge, so in the next few minutes, I'll try to briefly summarize the problem and then highlight some of the research and implications related to global ocean warming. By now, you're probably well aware of the factors that contribute to climate change, but if not, I'd encourage you to explore the Intergovernmental Panel on Climate Change, or IPCC, reports, which are an excellent source of accessible and extensively peer-reviewed climate and ocean science. One aspect of climate change that I find frequently surprises people is that the ocean has taken up more than 90% of the excess anthropogenic heat of the climate system. On the face of it, this may seem like a good thing, leading to less atmospheric heating, but as we'll see, that's not the case. These two plots from the IPCC Fifth Assessment Report summarize how the global ocean is warming. The plot on the left shows the evolution of globally average temperature difference from the mean of the top 700 meters of the ocean. And the map on the right shows the temperature trend of the top 700 meters over the same period. The IPCC, in conjunction with thousands of scientists around the world, conclude with certainty that the surface ocean is warming. And it's fair to ask how we know this, so let's explore some of the research behind this conclusion. Ocean temperature observations date back a very long time. Coastal observatories, ocean moorings, ship, and more recently, autonomous glider transects all record data at various locations and over a wide variety of depths. The observed ocean area vastly expanded in 1979 when satellites began to observe sea surface temperature. Modern satellites fly in coordinated orbits, making a wide variety of observations from the top of the atmosphere down to the surface of the ocean. And these data are publicly available, and I'd encourage you to go check them out. For example, a recent global sea surface temperature observation from the MODIS Observatory on the Aqua satellite is in the lower right. Satellites observe only the surface ocean, however, and observations in deeper water are sparse, which is why the Argo program was initiated and has become so important. Since 2000, Argo floats have provided continuous observations of the ocean's top 2,000 meters. And as of a month ago, there were nearly 4,000 operational floats deployed by 24 different countries throughout the world. These data are also publicly available. So here's a plot from an instrument that I pulled at random, not too far away from where I am now. This plot shows depth on the y-axis plotted versus temperature, and it clearly shows the classic ocean temperature profile with warm, less dense water floating near the surface and cooler, denser water below. Of course, these data can be used to study many different processes, but how are all these measurements used to study global ocean warming? From a global ocean warming perspective, scientists are basically trying to understand three fundamental things. And that's, what is the heat flux through the ocean surface, both into and out of the ocean? How much heat is contained near the ocean surface? And at what rate is surface ocean heat mixed into the deep ocean? And these are three really important questions. The first question addresses how much heat is entering or leaving the ocean system. The second question addresses the temperature and habitability for organisms in the epipelagic or sunlight zone, where most of the ocean's biomass is contained. And the third addresses the rate at which the entire ocean heat content is changing. So let's now talk about a few implications for a warming ocean. Sea level rise is a direct consequence of the rising ocean temperature. As water temperature rises, the volume that water occupies increases related to the thermal expansion coefficient. And you can actually explore this and determine the thermal expansion coefficient for yourself. One experiment that I like is linked at the bottom. Sea level rise is a topic of another talk, so I won't say too much more about it other than to point out that thermal expansion is a significant contributor to the observed global mean sea level rise. Another direct implication of global ocean warming is increased stratification. As the surface ocean warms, the surface layer becomes less dense, and the ocean becomes more stratified or harder to mix. Intensified surface warming has increased thermal stratification of the surface ocean by about 4%. And this map indicates the rate of stratification change around the world. Increasing stratification and the subsequent reduction in mixing is troubling, since oxygen-rich near-surface waters are less likely to be mixed downward, and similarly, nutrient-rich deeper water can't be mixed to the surface photic zone where primary production can occur. Thus, increasing stratification is very likely to reduce primary productivity and fish stocks, according to the IPCC. And again, there are several experiments that you can try yourself to see how increasing stratification inhibits mixing. This is an experiment from the University of Maine that I particularly like. Marine heat waves are defined in a few different ways, but are essentially prolonged periods of abnormally warm water, partly due to the increased stratification and partly because of the extra heat in the climate-ocean system. Marine heat waves have doubled in frequency, become longer lasting, more intense, and more extensive. The IPCC concludes that 84 to 90% of the marine heat wave events occurring between 2006 and 2015 were due to anthropogenic temperature increase. Here, the plot on the left highlights some of the more recent marine heat wave events and their attributable costs. Like ocean temperature in general, marine heat waves have far-reaching effects, even causing droughts, floods, intensified storms over land, in addition to the direct ocean ecosystem impacts. And you can monitor marine heat wave conditions on your own. For example, this map shows conditions recently on November 5th. Finally, let's look at how the global ocean temperature is expected to affect a wide range of ocean ecosystems. The plot here in the upper left panel shows the global mean sea surface temperature versus time. The brown line is the observed temperature with the current warming level above pre-industrial temperature, shown by the horizontal gray line. The red and blue lines represent predicted temperature under two different climate mitigation scenarios. The red line is the predicted sea surface temperature under a business as usual scenario, basically doing nothing. The blue line represents the predicted sea surface temperature with aggressive climate change mitigation measures in place. The remaining colored bars here represent the degree to which ocean warming affects various ecosystems, with white representing undetectable effects and healthy ecosystems, and purple representing a very high ecological risk. So today, we're documenting adverse effects to the epipelagic, salt marsh, seagrass, kelp, and warm water coral ecosystems with high or very high confidence. But in just 30 years, at our current level of warming, all ecosystems, including the deepest parts of the ocean abyss, will likely be affected, with the most biologically productive and diverse ecosystems affected at high or very high levels. So that's just a very brief tour of the global ocean warming problem and some of the science behind it. The problem, like any potential solution, is complex, it's far-reaching, it's tied to climate change with impacts to global economies. And if there's any silver lining to anthropogenic climate change and global warming, global ocean warming, it's that it's anthropogenic. We changed it so we can affect change. And I've left this plot up to emphasize that point. There are personal choices that we can make to help mitigate both atmospheric and ocean warming, from eating lower on the food chain to simply being aware of and reducing how much energy and material we consume. We can also prepare for expected changes, such as sea level rise. And importantly, I want to emphasize that it's individuals who first spark systemic change, and that has real potential to move the climate needle. And ultimately, climate mitigation will involve governments, industry, and individuals, but science needs a seat at that table. And all of us can be an advocate for evidence-based science. The IPCC reports are a great place to start if you're new to the topic, and I encourage you to go check them out. I hope you found this talk helpful, and as you listen to others related to climate science and ocean science, I hope you'll continue to think about how you can take action. Thanks.